So the curve C has equation y is equal to x squared plus ax plus 1 over x plus 2, where a is greater than 5 over 2. So on part A, find the equations of the asymptotes of C. All right. We get the vertical asymptote by equating the denominator to 0. So the vertical asymptote is x equals to minus 2. Okay, I hope that's okay.
Yes.
Then for the oblique asymptote, we can divide x plus 2 into the x squared plus ax plus 1. So dividing x squared by x, we get x, and x times this would give us x squared plus 2x. And we subtract, when we do x squared minus x squared is 0, ax minus 2x is a minus 2 of x, and we bring down 1, and we divide this by this x, and we're going to get a minus 2, and we multiply a minus 2 by this, and we will get a minus 2 of x. All right. And that's going to be plus 2a minus 4. All right. So we're going to subtract again, and we will get the remainder as a minus 2 of x minus a minus 2 of x is 0. 1 minus this should give us minus 2a, and that's minus 2a plus 5. All right. So that's what we have. But for the oblique asymptote, we just want the quotient. So therefore, the oblique asymptote is y is equal to x plus a minus 2. Okay, is that what you got for this?
Yes, I got that.
Good, that's fine. Now on part B, they say, show that C has no stationary points. Okay, now we have the original equation. We know that to find stationary points, we will do differentiation. So basically, since we have the equation as y is equal to x squared plus ax plus 1, so x squared plus ax plus 1 over x plus 2, all right, we will find dy by dx, because we know that at the stationary point dy by dx is equal to 0. So we'll differentiate quotients, that's x plus 2, of the derivative with respect to x of x squared plus ax plus 1 minus x squared plus ax plus 1 of the derivative with respect to x of x plus 2. And that's going to be O over x plus 2 squared, and we equate this to 0. Now, we will remain with the numerator, because if we multiply both sides by the denominator, it becomes 0 on the other side. So we will be left with x plus 2 here, and differentiating this gives us 2x plus a. All right. Are you following?
Yes.
Okay, good. Then that's going to be minus here x squared plus ax plus 1. And for this derivative, we just get 1. So it's all good. So this is all going to be equal to 0. Now we expand brackets here. And when we do, we'll be having 2x squared plus 4x plus ax plus 2a. And on this part, that's minus x squared minus ax minus 1 equal to 0. That's 2x squared minus x squared is x squared. So we have x squared, and ax minus ax is 0. So we are left with 4x, and the constants 2a minus 1. So it's going to be plus 2a minus 1 equal to 0. Now, do we have stationary points existing? Okay, because they want us to show that there are no stationary points. So let's test. We're going to do the discriminant. So for b squared minus 4ac, it's going to be, okay, let me do it this way. For what we have, we know that a is 1, b is 4, and c, the constant, is 2a minus 1. So therefore, for b squared minus 4ac, that's 4 squared minus 4 of 1 of 2a minus 1. Okay, which is 16 minus 8a plus 4, which essentially is 20 minus 8a. Okay, so 20 minus 8a is what we are getting. Now, 20 minus 8a, we're considering that the question tells us that a is greater than 5 over 2. So a is greater than 2.5. Okay, and we're saying since a is greater than 2.5 or 5 over 2, if you say 20 minus 8 times 2.5, you get 0. So anything greater than it, okay, you can try anything like 2.6, will always be negative. All right. So since a is greater than 2.5, 20 minus 8a will always be negative. Okay. Therefore, we can conclude that there are no stationary points on the curve C, because if we are having a stationary point, I mean b squared minus 4ac coming out as being negative or less than 0, it means there are no real roots, which means therefore there are no stationary points. Okay, do you understand this reasoning?
Yes, like I did up till the differentiation part by myself, then I
Okay,
didn't like I completely forgot how to like that I needed to do the discriminant. That's why I was stuck.
I see, I see, I see, I see. All right. Anyways, let's move on. So there's a part C here where they say sketch C, stating the coordinates of the point of intersection with the y-axis and labeling the asymptotes. Okay, so I'll draw two axes, the y-axis here and the horizontal axis here. I will put in the asymptotes. X is equal to -2 is the first one. So I'll draw it here, the asymptote. This is the vertical asymptote intercepting at -2 here. And we'll also have the oblique asymptote. The oblique asymptote is y is equal to x plus a minus 2. A is 2.5. I mean, it's greater than 2.5. Okay. So the y-intercept, 2.5 minus 2 is 0.5. So it has to be greater than 0.5. So basically, the intercept is positive. Okay. So the line will, remember, we're drawing the line y is equal to x plus a minus 2, right? X plus a minus 2. When x is 0, y is a minus 2. A minus 2 is anything greater than 0.5. Okay, so we'll just draw the line like this. And when y is 0, x will be 2 minus a. All right. Remember, a is anything greater than 2.5. So 2 minus anything greater than 2.5 should be something, it should always be less than -2. So it should be coming from a point like this, the one that we have. Okay. So I think we have drawn the line quite well. I'm going to do this. Okay. And we'll have the line being all right. Now we know that we have an oblique asymptote here, and we've also established on part B that there are no stationary points on C. So this is a type of graph. Since there are no stationary points, um, you know that it can either be a type of graph like this one, but this type here, will have stationary points, so that's not really the one. So it has to be this type of graph that we supposed to sketch. All right. And it should come like this. We have to understand where the graph intercepts the y-axis and the axis. Okay, we also need to be cautious of that. So let's really take a bit of care with that. For this original graph, okay, let me just copy it. Paste the equation here. All right. Um, for the curve, for where it crosses the x-axis, okay, let me just say when x is 0. When x is 0, y will be equal to a half. So it intercepts the y-axis at a half. Okay. So we know that it intercepts here. So I've properly drawn it. So I think that that actually helps. Okay. So this is actually how the graph is going to be. And the question had said we should also state the coordinates of the point of intersection with the y-axis. And we said it intersects the y-axis at a half on the y-axis. So the coordinates are 0 and a half. So that's how we do it. I don't know if you did the curve the same way.
I did the curve the same way. Yeah.
Okay, that's good. Now on part D, that's D part 1, they say sketch the curve, which is essentially the modulus of the curve above. I'm going to do it this way. Okay, so this is the graph we had right above, and I'm going to reflect the part of the graph that is below the x-axis, all right, in the y-axis. So this line segment will come out like this. It's not a straight line, it's a curve. So I think if we do it this way, it should be good. So we've reflected this line segment. So I'm now going to erase it. Okay, so it's no longer here. All right, something like this. And this other line segment, we reflect it in the x-axis. Let me use so it will be like this. So let me erase it from down below. Okay. So this is what I'm getting right on here. All right, that's the type of graph I am getting. Did you get a similar graph for the modulus graph?
Yes, I got the similar one.
Okay, good. So yeah, just increase the size a little. Okay, let's move on to the next, okay, on part 2 here, they say on your sketch in part 1, draw the line y is equal to a. Draw the line y is equal to a. All right. A is greater than 2.5. So it can be a line like this, a horizontal line. So this here is the line y is equal to a. That's the line y is equal to a that I've just drawn on the graph. Now, on part 3, they now say it is given that mod of the function is less than a for these values and those values. Find the value of a. All right. Okay. All right. So quite an interesting question it is. For mod of x squared plus ax plus 1 over x plus 2 being less than a. All right. We are going to, it's a modulus inequality. So we're going to have for its solutions, x squared, we're going to consider x squared plus ax plus 1 over x plus 2 is equal to plus or minus a. So essentially, we're going to say it is going to be equal to minus a, and it is going to be plus ax plus 1 over x plus 2 is equal to positive a. All right. So this is essentially what we have. So what this really means, okay, or maybe another way to look at this would be to say, if you look at the line segments we have, the line segments which I'm highlighting in red are the ones that were reflected. Okay. These are the reflected line segments, and the one that I've kept in black are the ones from the original. So the ones from the original are the ones from the equation, okay, the ones represented by the bold black line, are the ones for um y is equal to x squared. Okay, let me write that down. Y is equal to x squared plus ax plus 1 over x plus 2. And the ones in red, okay, the ones I've just are the ones for are reflected. So they are minus of x squared plus ax plus 1 over x plus 2. So that those are the two line segments we got. But they're intersecting with the line y is equal to a, right? So we want the points of intersection with the black line, which are this point, and this point. And we find this by saying x squared plus ax plus 1 over x plus 2 is equal to, it intersects with y is equal to a, so it's equal to a. So that's what's equivalent to this equation. All right. And where the line y is equal to a intersects with the red line, this one and this one here, is where this, which is minus of x squared plus ax plus 1 over x plus 2 intersects with the line A, which is the same as we can take the negative sign to the left and we say this is equal to minus A. So this equation is equivalent to this. So basically what we're trying to do is to find those points of intersection. Okay, are you tracking?
Can you repeat the last part about how like which equations mean what? Because you said um just the last thing you said.
The last thing you mean do you mean for this equation here? Or
Yeah,
even,
like those two equations and which, like, you know how you connected it with an arrow? Like, can you explain those? Like,
okay, it's fine. It's all right. It's perfectly fine. So the basic thing here, not so complicated. The basic thing here is what we are seeking to do, okay, and we know that that's gonna help us to find the value of A as they want. We want to find the points of intersection. Okay, we have 4 points of intersection, right? So for the first two point of intersection, this, I don't know, let's call it alpha and beta. Those are the points of intersection of this curve and the line y is equal to A. So that's why I equated those two. All right.
okay.
And I was saying this is the same thing I had written here already.
Oh, okay.
Mhm. And the other one, um, other points of intersection are this one here, which we can use, I don't know, a gamma, and this one will be, what other Greek letter? Sigma
Delta.
or delta, yeah. Delta would be, those two. So that's when this graph intersects the graph y is equal to A. So that's why I equated the two here. And this equation
Oh,
is the same as this one here.
okay, I got you.
Okay, good. Okay. Anyways, let's carry on. So let's see how if we can make sense of what we have. So essentially, because we'll need to economize the space we have because we have little space here. We're going to, multiply both sides by x plus 2 here. So x squared plus ax plus 1 is equal to minus ax plus minus 2a, right? Minus 2a, which is x squared plus 2ax plus 1 plus 2a equal to 0. Here we get x squared plus ax plus 1 is equal to ax plus 2a. So x squared and ax minus ax is 0. So it's plus 1 minus 2a equals to 0. Okay. So this is what we are having right on here. And this one is easier to work with because we can say x squared is equal to 2a minus 1. So x is equal to plus or minus the square root of 2a minus 1. So for this one, we're good. All right. For the other one here, so we have to do the formula, quadratic formula, minus b plus or minus the square root of b squared minus 4ac all over 2a. All right, so that's minus 2a plus or minus the square root of 4a squared minus 8a minus 4. So this is what I am seeing here, all over 2, okay, which is essentially, if we divide everything by 2, we get minus a plus or minus the square root of, and if we factor out 4 on this, square root of 4 is 2. So we are just left with a squared minus 2a minus 1. Okay, so these are the roots we have. So we now have the 4 roots. Okay, all right. Now, according to the question, okay, the solutions we should get, okay, for the inequality. Let me remove this to make sense of this because we're almost done. Okay, but I really want you to understand what's going on. Okay, so to solve this equation here, Amira, it's the modulus graph is less than A. Okay, the modulus graph is less than the graph of y is equal to A. That's how you should view this. The modulus graph is vertically below the graph of y is equal to A. So our solution should be what I'm highlighting in yellow. These parts of the graph are the parts that are satisfying the inequality. Okay, let's just use the letters, even though they're not in any good order. Okay, but I have gamma, alpha, delta, beta. Okay, so the solutions are essentially values of x that are between gamma and alpha. So from gamma to alpha, sorry, that's alpha. From gamma to alpha. And the other set of values satisfying this inequality are from delta to beta. So those are the two solutions. Okay. Let's look at these. Okay. Let's start with the first one, gamma to alpha. Okay, just hoping that I don't complicate things for you, but we're almost there. Okay. So copy. Let's bring it down here. We have little space, so I'm going to create a bit of space here. Okay, so the solutions. The first one is gamma to alpha. Okay, what is gamma and alpha? Gamma is the solution, the red solution, all right? The red solutions are the ones for the reflected. Okay, so the red solutions are the ones where they intersect with the reflected graph. So these are the ones. These are the red solutions. So where the red line, the lower one is minus a minus, so let me write that down. That's minus a minus the square root of a squared minus 2a minus 1. And it's less than x and it's less than alpha is this point here, the black solution where the original graph intersects. So these are the solutions we got for the black intersection. So then the negative one minus, so this is supposed to be minus the square root of 2a minus 1. So these are the first solution. And then the second set of solutions is this one here. That's from gamma to delta to beta. So delta to beta. Delta is this point here, which is reflected, the red intersection, the higher point, which will be minus a plus the square root of a squared minus 2a minus 1 less than x less than beta is the positive one here. That's the square root of 2a minus 1. So these values that we've gotten are comparable to this and this. Okay. The first solution is minus 5 minus root 14 is less than x is less than minus 3. And the other one is less than 3. So we can take any one, okay? We are now saying that, say, for example, if we take this 3, it corresponds to the square root of 2a minus 1. So we can just say 3 is equal to the square root of 2a minus 1, square both sides. So 9 is equal to 2a minus 1. So 10 is equal to 2a. Therefore, a is 5. So this is the answer. That's the value of a. Okay. Well, I don't know. It's a bit of a wild question, but I don't know if you understood what I did here.
I understand.
You do. Okay. Perfect. Perfect, perfect, perfect. Now we need to move on to the next question, which is question number 7.